In section 6.1 videos that you watched on my math lab, you learned about greatest common factor. First, finding the greatest common factor for a list of integers, also finding greatest common factors for algebraic terms, and then eventually finding greatest common factors in a polynomial, factoring out the greatest common factor from a polynomial, or factoring out two different greatest common factors by grouping polynomials into smaller groups of terms and then taking out their greatest common factor. Well, the whole reason that we learn factoring is that it's one of the steps that we need in order to be able to solve polynomial equations. So 6.1 looks at polynomial expressions. In section 6.6, you're going to be asked to solve equations using these techniques that you learned in 6.1. So let's talk a little bit about how that would work. The first thing that we need to discuss is the zero factor theorem. The zero factor theorem is the rule in math that says if A and B are real numbers, meaning that they are whole numbers or fractions or negative numbers, any kind of decimal number, if both A and B are real numbers, and if their product, if when you multiply them together you get 0, then either the A or the B has to be 0. There's no way to get an answer of 0 for multiplication unless one of your factors is also a 0. So in this first example, 3 times 0 is what would give us 0 as our answer. The same holds true for fractions. In order to get this equation to be true, the number that the 1/2 is being multiplied by would have to be a 0. And the same is true when we're working with integers. If we want the answer to this equation to be 0, the only value that we can put in that blank spot is a 0. So let's look at how that applies to a factored polynomial. So right here you've got a polynomial that's already been factored by grouping into x plus 9 and x plus 17. If we use the zero factor theorem, we're saying that both of those factors, that either the x plus 9 or the x plus 17, has to equal 0 in order for this to be a true statement. So the way we solve this is by setting x plus 9 equal to 0 and x plus 17 equal to 0 and seeing what answers we get. We'll subtract 9 from each side and get x equals -9. Over here, we'll subtract 17 from each side and get that x equals a -17. Now let's check that answer to prove that those two answers really are true. So first I'm going to check the x equals -9 by substituting in -9 for both of my x's in this equation. I'll get -9 plus 9 times -9 plus 17 equals 0. Well, -9 plus 9 is 0, and -9 plus 17 is 8. And sure enough, 0 times 8 is equal to 0. Checking my other possible solution, the -17, I'm going to write -17 plus 9 times -17 plus 17 is equal to 0. And when I add these together, I get a -8. -17 plus 17 is 0. So I have -8 times 0, which is also 0. So both of those answers check out. What I want you to notice here is that in linear equations, when we were solving equations that only had x to the power of 1, we only got one answer out for x. You'll notice now that we have a quadratic equation, because if we multiplied this out, if we FOILed it, it would go back to being x squared plus 9x plus 17x plus whatever 17 times 9 is there. See how this x is to the power of 2? That means we're going to have up to 2 correct values for x if it has a distinct solution. So we're looking for 2 answers for x when we're dealing with x to a power of 2. This next problem has a little bit more algebra to do in the solving, but you can see it's already factored into two binomials. They are already set equal to 0. So we're going to use exactly the same process we used up here. 3x minus 2 equal to 0, or 5x plus 1 equal to 0. Solving this first one, I get 3x equals 2, divide both sides by 3, x is equal to 2/3. And solving the next equation, I'll subtract 1 from both sides. I get 5x equals -1. Divide both sides by 5. X is equal to a -1/5. So again, two possible answers. In this next example, we need to use a little of the factoring that you learned in 6.1 before we can solve it. So looking at this equation, I have an x squared term and a 15x term. So there is a greatest common factor there of x. Both of the terms contain at least one x. So I'm going to go ahead and factor that x out and rewrite this equation as x times the quantity x plus 15 equals 0. Now I have an expression or an equation that I can apply the zero factor theorem to, because I have a first term, which is my x, a second term, my x plus 15, they're getting multiplied and they're equal to 0. So the zero factor theorem has to apply to this equation. So when I split it up into the two pieces, I get x equals 0, or I get x plus 15 equals 0. Solving this one for x, I get x equals -15. So the two possible solutions for this polynomial equation are x equals 0 and x equals -15. In our final example for this section, we're going to look at one where we have to do a little more rearranging before we can solve it. I'm going to fold my paper down here so you can see this. So again, we want to apply the zero factor theorem. But notice, for the zero factor theorem to work, we have to have multiplication as our operation, and our equation has to equal 0. So we've got some math we've got to do on this one before we're going to be able to do that, because we do have a product. We have 5 times another term, but it's not equal to 0. It's equal to 9. So I'm going to do the algebra to distribute the 5 onto the 13 and onto the 4x, and move that 9 over to the other side. Oh, actually I don't have to do that. Guess what just happened? They've snuck in a linear equation. We don't need the zero factor theorem because we only have one x to search for. There aren't two x's. So I can just solve this the way I would solve any linear equation. I went ahead and distributed. I'm going to bring that 15 to the other side and get -20x is equal to -6. Divide both sides by -20. And running out of space, I'll put the answer over here. X equals a positive 3/10. If this caught me, it's probably likely to catch you. Do be aware that in this textbook they do sometimes circle back around to a topic from an earlier chapter to make sure you haven't forgotten the rules you've learned there. So if you only have x to a power of 1, go back and use those rules that you learned for linear equations. And that's the end of our instructions for the 6.6 problems that accompany section 6.1.